Good. I thought that was a good way to start this topic. Now, gents, this booklet we're going to spend a good rest of the trimester on. Our test is likely to be Monday or Tuesday of week 5 because then you lot disappear on the Wednesday onwards, getting ready for venture. So if it takes us till the end of next week, then so be it. If we need another lesson, then we might steal the Monday's lesson. Okay. Now, this section is not really in the Year 10 syllabus per se, but it is quite interesting and it is relevant to why we need redshift and emission spectra, which is in the course. But this is a little one lesson backstory. So, gentlemen, we need to look at the size of objects that appear in the night sky. And at the moment, in 1 degree, if you held your thumb out at arm's length, your width of your thumb occupies about 1 degree of angle in the sky. So it has an apparent angular diameter of 1 degree. For most people with a standard length arm and a standard sized thumb, it's about 1 degree. You could figure it out, gentlemen, if you did the arctan of opposite over adjacent, your calculator should spit out a number close to 1. But there are objects in the night sky that are a lot smaller than 1 degree. So we need to split our degree into 60 and we get an arc minute. So if we said 1/60th of a degree, that's called 1 arc minute. Okay? If we then took another 1/60th of 1/60th, what am I trying to write here? I should be looking at my screen. We would get 1 arc second. So obviously 1 arc second is 1 over 3,600 of a degree. If you took a degree, which is about your thumb, sliced it into 60 even segments, each segment is 1 arc minute. You slice that again into 60, you've got 1 arc second. Okay? The moon, as a rule of thumb, is about half a degree in the sky. So if you go outside and look up at the moon, put your thumb at arm's length, the moon would be roughly half the size of your thumb. It occupies an angle of 30 arc minutes or half a degree. Okay? So there is a diagram. Did I remove that from you? No, it's there. There is a diagram of the moon. Okay? I might make it a lovely grey colour. Okay. Now, let's just do a quick little bit of maths. As I said, it's arctan opposite over adjacent. If we said a person stood 110 meters away, which is 1,000 meters away, okay, that could be from here. That might be looking outside and looking at the. There's 2 apartment blocks on the other side of Stirling Highway. The one at the front is a little bit derelict, and then there's a nicer one behind it. That nicer one behind it is about 1,000 meters away. So imagine you looked up and there was a person standing on their balcony. What would 1 arc second look like in terms of the size that it appears? So we're going to draw a little dashed line. And we're asking for what the size would be if this angle was 1 arc second, or 1 over 3,600 of a degree. Okay? So we do our little maths. Tan of 1 on 3,600 equals x on 1,000 meters. Therefore, x equals 1,000 tan of 1 on 3,600. And we get a number around about 0.0048 or 4.8 millimeters. So what that means is if I stood 1,000 meters away from you, 4.8 millimeters is about the top of my watch face to the bottom of my watch face. So if I stood 1,000 meters away and held out my Fitbit screen, from the bottom to the top is an area of 1,360th of a degree. Okay? we need to make very, very precise measurements of angle, and we can with telescopes. And we can use this phenomena called parallax. So we're going to use parallax, which is a phenomena that occurs, and the measurement of arc seconds, which are very, very precise measurements. Now, please hold out your thumb again. Now, please, close one eye and block my face with your thumb. Now, change eyes. Change eyes, close the other eye, open the other eye, close. All right, now I have appeared to move, like Robert. Robert has, calm down, making measurements. Robert has appeared to move. Now, if I know one side length, I could measure the angle that Robert has appeared to move, and that's called your parallax angle. Now, here's the cool thing. If I know the distance between my two eyes, which I can, with the help of a friend, I could measure my pupillary distance between my two pupils. And if I then measured that parallax angle, I could use some geometry to figure out how far away Robert is from me, okay? But how would I know how Robert has appeared to have moved? Well, oh, hang on, sorry, it's the thumb. Hang on, wait. Let me track back. I've gone off course. If I measured the angle that my thumb has moved relative to Robert, all right, then I've got my baseline, and then I've got my angle to my thumb. I can figure out the distance to my thumb. If I know the angle that my thumb has moved from one eye to the other, one measurement to the other, and the baseline, we can figure out. The key thing here is that Robert needs to be really, really, really far away, because I'm taking a measurement based on where Robert is, and I'm trusting that Robert hasn't really moved. And he would have slightly. I could do the same thing and say, well, Robert's hairline just appeared to shift to the back of the room, but not by much. So for this to work, the background, which is Robert, has to be really, really, really far away, and whatever I'm measuring needs to be much closer. And that's useful for us in the universe. Many stars are really, 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 really far away. Okay? So don't draw this diagram, but have a look at this wonderful little diagram I'm about to draw on the board. Here are some distant stars. Okay? Lovely stars. And there's one star there. And I measure where that star is down here on Earth. I'll say Earth, like so. And I measure the angle that it appears in the night sky. Now, our sun, 6 months later, I'm over here. So I take my measurement, and then I go on my orbit around the sun. I'm a certain distance away, and then but that angle is with reference to the background star. Okay? So I would say, oh, yeah, that star there, it just seems to be right next to that star there. Okay? And then, 6 months later, I take the same measurement, and all of a sudden, it appears to have shifted. It's no longer next to that background star. That background star is a certain amount of angles shifted. Okay? Now, if I know this baseline, which we do, and I measure it, well, should really have looked at something that's in the middle, but if I then measure that angle, then I can figure out the distance to the blue dot. The diagram doesn't really work very well, but I want you to write down let's write down the following. Here's the sun, and we've got our Earth, which is separated from the sun by 1.5 by 10 to the 11 meters. It's about 150 million kilometers away from the sun at any one time. Okay? So again, our baseline, it's actually 1.50 to 3 significant figures. Okay? So again, if we have our unknown object up here, and we measure our angle with reference to our background, stars, then we can figure out our distance d. Okay?
Is it from that to the sun or from that?
Pretty much to the sun. And what we'll find what we will find, Mahoney, is that the distance D, this is not to scale, okay? But that length, that side length D, is going to be so much greater than our baseline. This angle is going to be really, really, really small. So on the diagram, this looks like 45 degrees. Well, no, we're not going to see a star suddenly shift by 45 degrees. It's going to shift by, we're talking arc seconds in the night sky. So your astronomers are taking very, very precise measurements of where that star appears, and then very, very precise measurements of how it appears to shift. Okay? Now, the reason I brought into parallax is because there is an astronomical unit called the parsec. Its symbol, it's a unit abbreviation, lowercase p, lowercase c. Now, a parsec is the distance required for a subtended angle of 1 arc second with a baseline of 1 astronomical unit. Now, the astronomical unit is the distance that we use between the Earth and the Sun. So I said before, that is 1 AU. 1 astronomical unit. 1 AU, 1 AU. Okay? Yes?
Is that the distance from like the centre of the Earth to the centre of the Sun, like the closest part of the Earth?
Well, again, it would be centre to centre. 10 to the 11 is many, many orders of magnitude greater than 10 to the 6, 10 to the 7. That's the size of our Earth. That's comparing us, a millimetre to a kilometre. So it's normally the centre to the centre. Now, remember I said, this angle here is 1 arc second. So if you could just write here 1 over 3,600 of a degree. So remember I said that the angle of 1 arc second, if you stood 1,000 metres away, 1 arc second would subtend the height of my watch face. Okay? Now, if I doubled the distance, I would get 2 lots. If I stood 2,000 metres away, that angle would subtend 2 lots of my watch face. If I went 10,000 metres away, it would subtend 10 lots of my watch face, 4 centimetres. How far would I need to go back so that the subtended height was the distance between the Earth and the Sun? A really, 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 really far distance. Okay? Let's calculate that. Trillions. Let's calculate that. Let's draw another diagram similar to that diagram there. Let's draw our Earth and our Sun separated by 1 AU, and then let's go a certain distance away and call that 1 parsec, such that this angle here was 1 arc second or 1/3600 of a degree. Okay? We're going to do our equation again. That 1 parsec is 1 AU divided by tan of 1/3600. And if you do that, you get 206,265 AU. That's how far back you need to go in terms of the mean Earth-Sun orbital distance. Now, we already had a conversion that 1 AU was 1.5 by 10 to the 11 meters per AU. And absolutely, if we multiply, we'll get it in meters. That's 3.09 by 10 to the 16 meters. Okay? Now, I've given you a little fact file, info file from Wikipedia, just over here. Could you do the following? Get your white out or your red pen and just cross out this one. Bloody Americans. Alright? I know. Hurry up. It's 2017. Adopt the metric system already. Now, We've just figured it out in meters, and we've been given it in other astronomical units, AU. Let's go light years, though. So what we're going to need to do, a little side mission, figure out what a light year is. So 1 light year is the distance that light travels in the period of 1 year. Now that's going to be 1 LY. Now that's going to be c times t. Listen up, please. C is the symbol for the speed of light in a vacuum. Okay? I believe it came from the Latin word ceres. I think it's Latin for light. No one really knows. I think that's it. Everyone always asks, why is it the symbol C and not V? Well, any time you see C, boom, speed of light in a vacuum. It's 3 times 10 to the 8 meters per second, and we're going to get the time of a year in seconds. So we're going to go 3 by 10 to the 8 multiplied by 365.25. That's many days in a year. This is how many hours there are in a day, minutes in an hour, and seconds in a minute. And we get 9.47 times 10 to the 15 meters per light year. Okay? Now, in fact, I'm just going to write up here, we have meters per parsec and meters per light year. I want to get meters per parsec over meters per light year. If I divide meters per parsec by meters per light year, we get light years per parsec. So I'm going to take our top number, which was 3.09 by 10 to the 16, divide it by our 9.47 by 10 to the 15, and we get 3.26. Light years per parsec. Let me just make some room here. Okay. So again, if I could get on this special spaceship that could travel at the speed of light, not possible, but let's just imagine, I travel away from the Earth at the speed of light, I travel for 3.26 light years, I turn around, and the Earth and Sun are now separated by a distance of 1/3600th of a degree. Okay? Now, parsecs seem to be an astronomical unit which is easy to refer to. Our nearest star, Alpha Centauri, is 4-point-something light years away, or we could say that it's 1.5 parsecs. Okay? There's a term, I think it was Han Solo was able to do the something run, the Kessel run, in 12 parsecs. And many people said, hang on, he's saying I did it the fastest. He's saying, and a lot of people argued that it was wrong, saying, hang on, he's talking about a unit of distance. Shouldn't he be talking about a unit of time? But in the Lucas world, in the Spielberg world of Star Wars, the Kessel Run? The Kessel Run was getting from one star to another, going through raider territory. So there's an area in between which was notorious for raiders, baddies in spaceships, and they would come like pirates and steal all your stuff. And so obviously the most treacherous route was the shortest path. So people would go around the star, around the region, and travel a greater length of parsecs. He did it in the shortest distance of parsecs, which was the more dangerous in the Millennium Falcon.
So
makes him a better pilot.
I thought you were saying Castle
Makes
was
chewy.
the entire time.
Makes chewy.
I thought it was.
Alright.
Alright. Saying I can travel 12 parsecs.
Gentlemen, turn over the page.
That's what I was saying.
Now,
I thought he was saying this entire time.
Please. Proxima Centauri, which is the star cluster, is definitely 4.24. Oh, that is the star in Alpha Centauri. No, wait. Proxima is the star, Alpha is the cluster. This one is the closest of them. 4.24 light years away. That is correct. I may have made up the 2 milli-arc seconds just for this activity. So, what we're going to do is we're going to set theta to 2 milli arc second.
So small.
Okay? And that's going to convert it into degrees. Now, you could do this in your calculator, and you would basically just get a decimal value of a degree. We're talking 10 to the negative 5 or 10 to the negative 6. Okay? So that's how, even though we see the starlight is bent and refracted and distorted as it passes through our atmosphere. If we went above our atmosphere and looked through, we would see it as a pinpoint, and it would be really, 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 really small in the light sky. We could still see it, but it would have a very, very small apparent diameter. Here's our diagram. 4.24 light years. We are asking for the base length, which is subtended by 0.002 arc seconds. Okay? So, since we're in light years, let's get our answer in light years. We would say our base length is going to be 4.24 light years times tan of our value. Okay, remember that's just a really, really small angle in degrees. Make sure you calculate it in degrees. And we get 4.11 times 10 to the negative 8 light years. Well, let's use our conversion of light years, 9.47 times 10 to the 15 meters per light year. Our light years will cancel and we'll get our answer in meters, which is 3.89 times 10 to the 8 meters. Again, that's huge. That's the size of a sun. Now, our sun's a little bit bigger. I made this number up. Our sun is about 100 times the diameter of the Earth. Our Earth is 10 to the 7. So really, we should be in about 10 to the 9 territory for a sun the size of ours. But even so, the size of a sun that far away is going to appear, we couldn't even measure, our eyes couldn't even perceive that small of an angle. Okay, it would need to be made with very precise, very high-powered telescopes that can move and measure differences in angles by tiny amounts. This excerpt was stolen/borrowed from Wikipedia. Space-based, okay, obviously, a lead into this paragraph, we were talking about the light does get scattered when it enters our atmosphere. It does diffract, it does get a little bit diffuse, it's not as sharp. So let's go above our atmosphere. Now, all of a sudden, that's like Mr. Murray without glasses. Mr. Murray puts his contacts in, you go from SD to HD, 4K, 8K, two 4K screens. You can make much, much more precise measurements. You can then resolve much, much greater distances. So basically, put a telescope in orbit around the Earth, have it looking as far away as you can, looking for measurements of parallax from one point in orbit. 6 months later, when you're on the other side of the sun, take your measurements again, and then you're getting very, very small parallax. Now, this is the most accurate. Hipparcos satellite in the 90s was 0.97. It could get up to 1,000 parsecs away. It could measure. The Gaia satellite launched a few years ago. It was going to do that many stars because, it's got to wait 6 months before it takes. So, take a few. What's that one? What's that one? What's that one? And then wait for 6 months and then do it again. 20 micro arc seconds. Okay, in measurements as far as the galactic center, about 8,000 parsecs away. Let's use that value. 20 micro arc seconds. Our tiny little primate brains cannot fathom how small of an angle that is. We cannot even fathom how large of a distance that is. But we've invented something called maths, or discovered, whatever your personal belief is. 20 micro arc seconds, whatever that is as a number. Oh, I've got it here. It's 5.55 times 10 to the negative 9 degrees.
Is it 5.56?
5.55.
Oh, really?
That's what I've got written here. So again, distance x, 1.5 times 10 to the 11. That there was 0.00001, 2, 3, 4, 5.
It is 5.56.
Yeah, it's 5 recurring. So.
Is it?
Yeah.
Why is it recurring?
I don't know.
Because you're dividing by 3,000.
Should I know that? I know dividing by 9 does weird stuff. Dividing by 11.
Yeah, because all of its prime, because the prime factorization isn't solely made up of primes. Isn't solely made up of 2s and 5s. So
True.
It's repeating.
I should have known that. Stupid. I'll go and give myself a thrashing. Good. X equals. I'm skipping all of the you know your Sokotoa rules. You can figure out what you need to do. Divide that by tan of 5.56 times 10 to the negative 9. We get 1.55 times 10 to the 21 meters. We are getting galactical now in our range. Let's use our light years. We're going to divide by 9.47 times 10 to the 15 meters per light year, and that will cancel out our meters, and we'll get a distance in light years. We get 1.64 times 10 to the 5 light years, or 164,000 light years. It is a lot of light years. We divide that by 3.26 light years per parsec, and we can get our answer in parsecs. We get 50.3 thousand parsecs. Okay? Now, what do you notice about that number?
Bigger than 8,000.
Absolutely nothing.
I know, right? Here's our Here is our galaxy. Composed kiloparsecs.
Oh god.
Well, so it said it only measures up to 8,000 parsecs.
Well,
We're so overshooting our mark.
Yeah.
So please tell me nothing is
not in the test, no. Gentlemen, our galaxy, the Milky Way, which when you look up at the night sky, you see that band of stars. You're actually looking from where we are.
Do you have to draw this?
Yes. Is about 100,000 light years across. It bulges in the middle, 10,000 light years wide, but near us. But, no, shush. But where we are, it's a little bit shorter. So it's like a spinning disk of stars. They're all spiraling around a black hole. And at the center of most galaxies, there is a black hole, which was once a very, very large star that ran out of juice and collapsed in on itself. Don't worry, our star is about 10% the required mass. All right, but at the center, if your galaxy has a large star, and they only last about 8 billion years, so you just have to wait, and then it'll go and die and turn into a black hole. Now think about all of those stars are basically analogous to water spinning around. You pull the plug out and the water will spin around like a whirlpool. The water falls in because it's losing energy due to heat and friction, but our stars are spinning around the empty void of space. There's no air resistance. So as long as they're traveling at the right speed, tangential to that black hole, they will just continue circling around, taking hundreds of millions of years to go around the center of the galaxy one time. Okay? Now, what we just figured out is that we can only really look within our own galaxy. So with our Hipparcos satellite, we're only going, oh, yep, there's a star, yep, there's a star. Oh, I can turn it around and go, what's over here? Oh, yep, there's a star. We're not even looking outside our own galaxy, okay? So we are limited to the 100 billion stars, on average, inside our own galaxy, okay? Now, I would like to show you a video, and I'm sure you are all familiar with Monty Python, the The Meaning of Life. Now, please tell me I put the link up. No. All right. We'll stop the screen capture because there's no need